So we said that stream ciphers try to produce a very long random looking key stream from a very short key. So the question arises as follows: how we can generate a very long random looking data from a very short random data? So for this reason, I'm going to talk about LFSRs first. Linear feedback shift registers, LFSR for short, are actually some of the time building blocks of stream ciphers. In almost in every stream cipher, people prefer linear feedback shift registers. So idea is as follows: assume that you have a state here, a register. So it can be as short as a few bits. So each box here represents a bit in this picture. So idea is as follows: every tick when you run this LFSR, the bit value here will be produced as output. Everything will be shifted one bit to the right, so this place will be empty. But what will be here in the following state will be decided from this initial state, which will be actually the XOR of the values of these boxes and added here. So which values are going to be XORed actually depends on the CI value. So if C1 is 0, for instance, there is no arrow here. If C2 is 1, there is an arrow here. So you are actually choosing tap points. And depending on your choice, the value that is going to be added here will be determined. So an LFSR is actually designed like this. You need only a few information, the size of this register, and the places where you have these tap points. So the values that are going to be XORed here. So LFSRs are very common in stream cipher design. So we are saying they are linear because we are actually performing a linear operation like an XOR operation. So if it were, for instance, bitwise multiplication and so on, then we will be calling them nonlinear feedback shift registers, and they're also used in stream ciphers. At one tick, the register produces one bit output. State is shifted one bit, and the new bit is obtained by the XOR of the bits of the previous state that has a tap point from the places that has a tap point. So this is a finite state actually because it is a finite size. So if this is m bits, then the internal state can take 2 to the m minus 1 different values. If it is all 0, then it becomes all 0. So this is why I'm saying that 2 to the m minus 1 different states. So from since it is a time varying transformation, the internal state will be changed from time to time, but it cannot change forever. After some point on, which is at most 2 to the m minus 1 different states, it will turn to the initial state which you started this. So it will repeat itself, of course, at most 2 to the m minus 1 times, which we call it the period. So I call it at most because if you choose these tap points in a bad way, and if you choose an internal state, initial state, and if you update it, for instance, a few times, and if it turns to the initial state, then this would mean that its period will be very short. 2 to the m minus 1 is the highest period you can get from an m-bit LFSR. So question is, what should I do to get this highest period? The answer actually depends on some mathematical calculations, but maximum period is obtained when the tap points are chosen according to a degree n primitive polynomial. So you choose an actually degree n primitive polynomial, and the degrees of the monomials in this polynomial will be corresponding to the tap points here. So in this lecture, we are not going to go into details, but that is the main idea behind it. So if you, from an n secret knowledge, for instance, if you have n bits, you can produce almost 2 to the n random looking bits by using again LFSR. But of course, an LFSR with such a simple design would not be enough to design a stream cipher, and it is not an easy task to give you a general picture for a stream cipher. So instead of it, I will show you a picture of a very simple but well-known stream cipher. So this way you can get the general idea behind the stream cipher. So this is A51 stream cipher. This is a GSM standard. It was developed in 1987. With 3G, actually, it became kind of a legacy algorithm, but as far as I know, it is still used. It doesn't matter if you are using 3G or 4G. The person you are calling, if the mobile phone of that person is old and does not support the new algorithm, which is actually the consumer algorithm, block cipher, then you will be talking with this very old algorithm, A51, which can be actually broken, which I will actually talk about in the following slides. But if you are using this cipher, then somebody can listen to your conversation real time by in the real time decrypting it. So it is badly broken. And actually, when you call somebody from your mobile phone, you don't choose which encryption algorithm you are going to use. So of course, default is the new standard, as I told you, the consumer block cipher. But it is this decision is actually up to the GSM operator, not to you. And if they force you to use A51, then you will be talking with A51 algorithm. An operator actually force you to talk in without any encryption at all. So you can send text, and anybody capturing the data from the air with an antenna would be listening to your communication. So most of the time, you don't know if your communication is encrypted, and if it is encrypted, which algorithm is used, you don't know. But as you can see, let's go back to our main idea. The idea was to show you a simple stream cipher. As you can see, there are 3 LFSRs here. You can see the tap points here. So all of them are chosen from a primitive polynomial. So all of them produces the maximum period. And this LFSR has size 19, this is 22, and this is 23. And in total, we have actually 64 bits here. So assume that you have filled the 64 bits with an initial value you chose. Once you run this cipher, so 3 bits will be produced from these 3 LFSRs. Their XOR will be produced as an output, and all of them will be updated themselves. Of course, the cipher is a little bit more complicated, and I will talk about it in the following slides. But as you can see, a very simple 3 LFSR are combined, and it became a standard encryption algorithm. So it fits on the screen with this figure. It is as simple as that. So it may be the case that the next state function does not depend on the plain text. In such a case, a key stream is produced by an output function G. Then the encryption function combines the key stream with the plain text. So next state function is something like this. It takes the internal state and the key and produces the next state. And output function actually takes the current state key and produces a key stream. And the encryption function just combines this key stream with the plain text and produces the ciphertext. So let me make this a little bit clearer by showing it on the picture of A51. Assume that you call somebody and you start talking. So what your mobile phone does is as follows. Using your key and the frame number, which is a 22-bit value that is chosen for that communication, are put inside this state. And this algorithm runs for some time to get it ready for encryption. So it is run a few hundred times, and the internal state. So these registers are filled with zeros and ones, and that will be your internal state. Then you start talking, and your voice is turned into zeros and ones. And from here, you are producing key stream, which is also zeros and ones. They are XORed with your voice and produced as the ciphertext. So this is what a key stream generator is actually. So this stream cipher is working as a key stream generator. You produce the key stream here. So this LFSRs are your actual next state functions, because the values here are your state, and they are updated with these LFSRs. Your key stream generator is actually the XOR of these three values. And your encryption algorithm is just the XOR of this output with your plain text, which is your actual voice while you are talking. So these three functions are defined like this. This type of stream ciphers are known as key stream generator ciphers. They have the advantage that the key stream can be pre-computed without using plain text or ciphertext. So this is an advantage. An important example is the binary additive stream ciphers, where H is bit by bit addition of the key stream and the plain text, which is the example I mentioned here. And block cipher mode of operations like counter mode actually converts the block cipher into a binary additive stream cipher. So remember the mode of operations we talk about in the counter mode, we actually encrypted the counters and produced some output. That is actually the key stream. You just XOR it with your plain text blocks and obtain the ciphertext. So this is why actually the person who wants to decrypt your message also encrypts the counters, but this time XOR this key stream with the ciphertext blocks and obtain the plain text. So this is why during those lectures I mentioned that these modes of operations turns the block cipher into a stream cipher. This was the main idea behind it. So we can actually classify stream ciphers into two. We can divide them into two classes: synchronous stream ciphers and asynchronous stream ciphers, which are also known as self-synchronizing stream ciphers. So idea is as follows: synchronous stream ciphers, due to some failure, might lose their synchronization, and they cannot recover it back. But asynchronous stream ciphers provide self-synchronization. That is the main idea behind it. So let's first talk about synchronous stream ciphers, and actually so far all of the examples I have mentioned are in this class. The types of stream ciphers we have considered so far belong to the class of synchronous stream ciphers. To use these ciphers, the sender and the receiver must be synchronized. So they must set the state at the same position. So your internal states must be the same with the people you are talking. Also, they must have the same secret key. But if the synchronization is lost, then the decryption fails. And the synchronization can be lost due to many factors like device failures, problems in the communication channel. This can be caused by environmental reasons. For instance, if you're if you're using GSM communication, if you go to the other side of a hill, then you might not get the reception. For this reason, the synchronization might be lost. Or maybe in your building, there's too much metal is used and Wi-Fi or GSM communication might fail. Also, there might be active adversaries where they insert ciphertext digits or delete your ciphertext digits, so they intentionally might break your communication. Actually, this is how jammers work actually. So how do you restore the synchronization? To restore decryption, additional measures have to be employed. You can do reinitialization. You can place special markers at regular intervals. You can try all possible key streams, but of course this is not a good idea, and so on. But of course the easiest thing is the reinitialization, which means as follows. Actually, we do it all the time in real life. When you're talking to somebody with on the phone, and if you cannot, at some point, if you cannot hear the person, but you know that they are talking, then this means that your synchronization is lost. So there's no point of trying to shouting and try to hear them. The easiest thing you can do, turn off the phone and call them back again. So this is reinitialization, and it always works. So I said that an active adversary might cause some problems. A modification of a ciphertext digit does not affect the decryption of the other digits, no error propagation. So by active adversary, we are talking about people who has control over the communication channel, so they can modify the ciphertext digits you are sending, or they can add or remove some of the digits. So this is what an active adversary is. Passive adversary just listens to the communication and obtains the ciphertext. As a result, an active adversary who delays or inserts ciphertext digits can be detected by the decryptor because the synchronization is lost, so you can no longer perform decryption. This way, you detect the active adversary. On the other hand, an active adversary may change the selected ciphertext digits, knowing the exact results of those changes on the plaintext. So, for this reason, some additional mechanisms must be employed in order to provide data origin authentication and data integrity guarantees. Let's talk about now asynchronous stream ciphers. When the key stream is generated as a function of the key and a fixed number of ciphertext digits, we obtain a self-synchronizing asynchronous stream cipher. So here the main idea lies at this word. We are using ciphertext digits for actually determining the next state or producing the key stream. So maybe we can give the functions like this, but important thing is as follows. Assume that there's an active adversary, so they deleted a lot of ciphertext digits, added or modified, but after some point on, they stop modifying your ciphertext digits. So after some point on, if you start receiving correct ciphertext digits, since your next state and your key stream will be determined by these ciphertext digits, this way you can produce the correct key stream, and since you obtain the correct ciphertext digits, you can combine them and obtain your plaintext. So after some point on, you restore back the synchronization. This is why we call them self-synchronizing stream ciphers. Since this decryption function depends on the k bit, which is fixed ciphertext digits, so not k bit, k digits, let's say, ciphertext digits, resynchronization is possible if ciphertext digits are deleted or inserted. So after some point on, if you receive k many correct ciphertext digits, you start decrypting correctly. The cost of resynchronization is a loss of a fixed number of plaintext digits. When a ciphertext digit is changed, inserted, or deleted, the decryption of at most k ciphertext digits may be incorrect, so there's a limited error propagation. But of course, we still need some additional measures to provide authentication and data integrity guarantees. So this is why after block ciphers, we talk about authenticated encryption. So message authentication codes or authenticated encryption actually solves this problem. So this was actually the reason why NIST actually in the lightweight standardization competition, they ask for authenticated encryption algorithms, not just block ciphers or stream ciphers. So let's look at the pros and cons of asynchronous and synchronous. Let's talk about asynchronous first. Each plaintext digit has an effect on all the remaining ciphertext digits in an asynchronous stream cipher. This implies that the ciphertext does not inherit the statistical properties of the plaintext, which is a good thing. As a consequence, asynchronous stream ciphers may be more resistant against attacks based on plaintext redundancy. Due to self-synchronization and limited error propagation properties, detection of an active adversary is more difficult than for synchronous stream ciphers because since the synchronization is restored, you might not know there is an active adversary. The input of the generator uses the ciphertext, thus the adversary has a partial knowledge about the variables being used, so this might be a bad thing. Of course, all of this are just theoretical talk. It depends on the design. But as the key stream depends on the message, these generators have a limited analyzability because we cannot analyze the algorithm. We want to check the quality of the key stream, but it depends on the message, the plaintext. So it is hard to talk about the quality of the key stream. A synchronous stream cipher attempts to capture the spirit of one-time pad by using a short key that generates the key stream which appears to be random, which we call pseudo-random. And here is also the same. Such a key stream is called pseudo-random. Much of the work in the field of stream ciphers is actually based on deciding what constitutes a pseudo-random sequence. In this context, key stream generator stream ciphers are evaluated by means of the quality of the key stream it produces. So let's talk about quality of a key stream. A key stream generator stream cipher is as secure as its output is closer to be a random. This concept can be understood in two ways. Is there some imbalance to the way the sequence is generated that allows the cryptanalyst to guess the next bit with some probability better than that of random guessing? So this is related with the appearance. Also, the second question is it hard to reproduce the sequence? This is related with the inherent complexity of the sequence. And how do we measure this? How do we answer these two questions? We said that first one is related to appearance and the second one is about complexity. For appearance, we have measures like period and statistical measures. So period must be very long or large, let's say, so that it shouldn't repeat itself. And statistical measures are actually statistical randomness test, which tries to check the quality of the key stream. So there, in literature, there are some randomness suites that you can use and check the quality of the key stream. But for the complexity, you can check linear complexity, max order complexity, or Lamp-Aziz complexity. And for linear complexity, for instance, there is Berlekamp-Massey algorithm, which just tells you what the linear complexity is. Actually, this tells you how hard is it to produce that key stream. So what is the smallest LFSR that can produce that key stream? The answer is actually can be obtained by Berlekamp-Massey algorithm, and which is actually a good practice to implement, actually.